Want me to do a couple more examples for you? I mean, I'm gonna anyway, and these are just a little bit more bizarre than the ones that preceded it. Okay, anyway, example 8. Determine whether the infinite sum from n equals 1 to infinity of the sine of 1 over n converges or diverges. So we've been trying to do like either a direct comparison or a limit comparison, so we need a comparison series. And we look at dominant terms usually, but what do we got here? We got the sine of stuff, and as far as that goes, it's not like there's a an n squared or exponential thing that's just obvious here. We're taking the sine of something. Anyway, well, okay, let's see if like the nth term test. Let's maybe try to apply that. So the limit as n goes to infinity of the sine of 1 over n. So think about this. As n goes to infinity, this is going to approach 0 right there, of course. And it goes to 0. And if that goes to 0, what's the sine of 0? Or getting closer and closer to 0, that's also 0. All right, so our nth term is going to 0. Nth term test for divergence wasn't terribly helpful. Is it positive? Well, doesn't the sine of something range from -1 to +1? It does, that is true. However, think about the terms itself, 1 over n. If you were to stick in 1, you got 1 over 1, that's 1 radian. And that's as big as this thing could ever be, 1 rad. Because if you stick in 2, it's a half a radian, a third of a radian, and then so on. So pi over 2 is what, like, it's about like 1.57-ish rad. Okay, and that on your unit circle is right up here. And then of course, your sine is going to be positive, right? 1 radian is the same exact length as this. Go wrapped around there. There's 1 radian, like right there. It's almost at the 1 o'clock mark on a clock. So that's a positive number. And this thing here is just, this angle right here is just approaching 0. It's always going to be a positive number. So we can conclude that these things are positive, which means, I mean, that's a good thing because we need that to be true in order to apply either the limit comparison test or the direct comparison test. So the next thing is what are we going to compare it to? Well, we do have 1 over n right here, which is the divergent harmonic series. Let's try that. Let's try comparing it to that series. That's the only thing it seems to resemble in any kind of way. Compare to it equals 1, infinity 1 over n, which is the divergent harmonic series. Don't forget your capital letter. Does it deserve an exclamation point? Probably it does not. Anyway, so let's do our limit then. So the limit as n approaches infinity of our series is the sine of 1 over n over the new series that we're comparing it to, 1 over n. Okay, if I take this limit here, I get, let's see, plug infinity here, I get 0, and then here I'd also get, we've already done this part here, the top limit is 0. So this approaches 0 over 0, which means that we're going to do L'Hopital's rule for real on this one. Take the derivative of the top, take the derivative of the bottom. So this should be equal to the limit as n goes to infinity of, I'll have to use the chain rule. So the derivative of sine of stuff is cosine of stuff, cosine of 1 over n. And now you need to take the derivative of 1 over n. And remember, we think of this thing as n to the -1 power. Taking its derivative is negative n to the -2 power. So it becomes times, here I'll put it in parentheses, -1 over n squared, right? And then you get the same thing on the bottom, -1 over n squared, which cancels out, fortunately, boom and boom. So we get just the limit as n goes to infinity of the cosine of 1 over n. Now, once again, this guy is going to 0. And what's the cosine of 0? That is equal to 1, which is finite and positive. Whoops, okay, positive. And I'm going to say that this time, for the sake of time especially, oh my gosh, I was talking about the sake of time and then I take the time to rewrite the word positive. Anyway, for the sake of time, I'm going to say that all of this is part of my conclusion here. I'm comparing it to the divergent harmonic series. I showed that the limit here was finite and positive when we took the quotient of those two things. Therefore, the series n equals 1 to infinity of the sine of 1 over n also diverges by the limit comparison test. And again, for the 4 billionth time, you don't have to necessarily write the limit comparison test as the test that you used. It should be obvious from all of the math that you've done. Let's look at just one more example, please. Just please. Okay, determine whether, look at this one. Look at this crazy business. It has powers of n here and then also an exponential in it. We want to see, is it going to be convergent or divergent here? Well, what if I just did this? I took the limit as n goes to infinity of n times 2 to the n over 4n cubed plus 1. Well, I'm pretty sure that this thing right here is more powerful than all of this other stuff right here. This thing is going to shoot off to infinity here, which means that this diverges by the nth term test for divergence. That's what it seems like to me. Okay, so I would pretty much stop there and say that that thing diverges. But let's say we didn't notice that. And let's boil this down to its most, I'm going to say its most dominant terms here. It's going to be all of this stuff over all this stuff. Forget the 1. Here I can also forget the 4 if you want to. And I'm going to go n times 2 to the n over n cubed. Cancel out a common factor of n, and I'd have 2 to the n over n squared. Okay, well, if you just look at that, this is exponential, this is power, which that thing is going to diverge by the nth term test for divergence again. I mean, still you have to establish it some kind of way. The limit as n goes to infinity of 2 to the n over n squared diverges, whoops, equals infinity. So the sum, I was about to write that and symbol again, n equals 1 to infinity of 2 to the n over n squared diverges. Right? Yeah, okay. Since that's the case, now let's go ahead and take the limit and just show that this thing is some sort of constant multiple of that guy, right? Ultimately a constant multiple. So the limit of ours as n goes to infinity, ours was n times 2 to the n over, oh God, I don't even remember, 4n cubed plus 1. And I'm going to multiply by the reciprocal of the one that we're comparing it to. So n squared up top and 2 to the n on the bottom. Cancellation, crayon, cancel, cancel. Okay, right, okay. Which is equal to the limit as n goes to infinity of, this was n cubed, right? When we multiply, 4n cubed plus 1. Powers are the same, so as far as the relative growth rates go, this is going to approach the number 1/4, which is finite and positive. So they do the same thing by the direct, limit comparison test. So therefore, the sum n 2n over 4n cubed plus 1 diverges by the limit comparison test. total overkill, honestly, because we could have stopped right there. If these terms right here are shooting off to infinity, there's no possible way that this series is going to converge. All right, so let's just wrap this up with a nice, neat summary of all the tests that we've talked about so far. So we just talked about the nth term test, and remember that this one is not for convergence, it's only for divergence. So here's what your series looks like. Of course, we take the limit of the nth term. If that thing is not 0, we know that that thing diverges. It does not show convergence. If it goes to 0, you don't know anything. It could still converge. It could still diverge. Who knows? Whatever. All right, then we looked at geometric. Look how I wrote that. See that magical O right there that's in red? Because this is the one that ordinarily starts at 0. If it doesn't start at 0, then when we talk about the sum, you have to make sure that you add in your first term or subtract it off or something like that. You got to take that into account. Okay. So the absolute value of your common ratio, if that's less than 1, we know that it diverges. If it's outside of that range, if it's greater than or equal to 1, then we know that it diverges. And here's the sum. Memorize that sum. The sum is equal to the first term over 1 minus the common ratio. And again, this only makes sense if your first term, like you start at 0. Let's say it started at 1, then just plug 1 into your little formula there and get your first term to plug it into the formula. Okay, the integral test. The integral test, your series is going to look like something that you can take and find a continuous function for, right? And we know that it's going to converge if we take the improper integral of that thing from 1 to infinity. If that thing converges, so does our series, and it diverges otherwise, right? But you don't know what it necessarily converges or diverges to. In order to apply that test, make sure that you point out that your function that you came up with is positive, continuous, and decreasing. And remember, the decreasing part you usually establish with some sort of derivative test, right? All right, p-series. P-series was based on the integral test, but it's a heck of a lot easier to establish. It looks like this, 1 over n to the p. And you could have a multiple out here, as we've done before. Maybe it's 3 times that. But anyway, when does that thing converge? It converges when your p is greater than 1, and it diverges when it is between 0 and 1, including 1. And notice how these things are sort of backwards from the geometric test right there. Okay, and then always have memorized that the harmonic series diverges. And then here are 2 new ones. The direct comparison test. So you have a series, and you got to have something to compare it to. And you have to establish that if it's going to converge, it's got to be smaller than a convergent. And if it's going to diverge, it's got to be larger than a divergent here. All right, limit comparison test looks sort of the same here. And then here we have to compare it to something that we know converges or diverges, but we are going to take the limit of the ratio, and it has to be finite or positive. If the original one or the one that we're going to compare it to converges, so does ours. If it diverges, the one we compare it to, then ours also diverges. And there you have it. There is a nice, neat summary. If you take a screenshot of that, have all of that stuff memorized, will all this stuff appear on your AP exam? Guaranteed that it will. All right, that brings us to the conclusion of our comparison test, the direct comparison and the limit comparison test, as ways to determine whether or not our series of positive terms converges or diverges.